Okay, so we have been looking at fatty acid synthesis. We've taken a look at the formation of some of the intermediates in the pathway. One thing that we want to focus on now is a very important enzyme in this biosynthesis pathway. Now, the enzyme is fatty acid synthase over here, and it has subunits over here. There are 7 subunits. We have 6 of those subunits that are enzymes, right? And then 1 is what? A carrier protein. A carrier protein. Now, we later know that this carrier protein is what? ACP. Now, the enzyme fatty acid synthase works as what we call a homodimer. A homodimer. So if you check this is one fatty acid synthase and this is another fatty acid synthase. But should they be able to catalyze the reactions that we'll talk about later on, then need 2 of those syntheses coming together. They dimerize. Now, looking at the structure that I have here, this is just a model. This is a structural division. So over here, horizontally, this is 1, and then this is 2. But function-wise, we don't have one fatty acid synthase catalyzing the whole pathway on its own, but it is divided. As you can see, there are 3 of the subunits over here, and then 4 over here. Then in this one, there's 3 over here, and then you have 4 over here. And so you can see that is what they are on flip sides. Now, I've also indicated here that there is a functional division, right? So this is the functional division. This is the functional division. This side, on the right side, you have what? 1, and then on this side, what? You have 2. So 1, 2, 3, 4, 5, 6, 7 are going to catalyze the formation of what? A fatty acid. And this one also will have what? A functional activity. So it will add there. So the same KS is the ketoacyl synthase that we see. MAT is the malonyl acetyl transferase. Somewhere you see that it is indicated as acetyl / malonyl CoA ACP transacylase. So elsewhere you see this name, but it is the same as the MAT, which is malonyl acetyl transferase. Okay, so now that we have looked at it, these are, we've mentioned 6 enzymes, and the carrier protein is what? ACP. Now let's continue. And one thing you also need to know that the 3 and then the 4 segments are linked by what? A segment that has 600 what? Residues. So these are the subunits, and then there is a link that is made up of 600 residues. That's what connects the 2 extremes of the fatty acid synthase. Now let's continue. Now, for the synthesis of fatty acids, our first major reaction is what? A condensation reaction. It's a condensation reaction. The second is reduction. The third is a dehydration reaction. And then the fourth is also a reduction reaction. It's however noteworthy that should the substrates acetyl CoA and malonyl CoA enter the synthetic pathway, they need to be armed with proper diester. proper thiester. So that's where the molecule ACP comes in. You have acetyl-CoA and malonyl-CoA, but with they being bound to the coenzyme A, they cannot enter what the pathway. So now our enzyme malonyl acetyl transferase, what does it do? It is going to exchange ACP for CoA. So instead of acetyl-CoA, you now have acetyl ACP, and then instead of malonyl-CoA, you have what? Malonyl ACP. Now, what happened here is that first, the malonyl does this addition, the ACP addition to the acetyl unit, and then ACP will now carry this substrate towards the very first enzyme active site. Enzyme active site, we'll look at that later. And then it will also come backwards and then get bonded to the malonyl and then send it to the same active site. And then allow for what? Catalysis to begin. Now, a little info on the acyl carrier protein, which is ACP. So, elsewhere, when you read, you see that sometimes they call it a carrier protein. Then you see a shuttle, and then elsewhere you see that it is called a theta. So this is a work that it does. It holds on to the intermediates in the pathway. So what it carries them and then sends them to the active sites, So that's the job it do. It does, sorry, that's the job it does. It carries the intermediates and then sends them to a different active site. It has what we call a phosphopanthethine group, to which the substrates or the intermediates are bonded. So this phosphopanthethine is having a sulfur hydryl group bonded to it. This phosphopanthethine is from pantothenic acid. So this way. So if this phosphopanthethine SH of ACP to be bonded to an intermediate, then we'll have the hydrogen going on. So if, let's say, it's supposed to be an acetyl group, it's carrying an acetyl unit. And if it's supposed to be let's say malonyl, then it will be carrying malonyl, and then carry them to the active sites. Now let's move on. We made mention of the fact that the very first reaction is a condensation reaction. So you understand that we have condensation reaction, a small molecule is lost. We have acetyl ACP plus malonyl ACP. Now, this reaction is going to occur at the active site of the enzyme beta keto acyl ACP synthase. This is where the synthesis is going to occur. Now, for the reaction, essentially it is two acetyl units, acetyl plus acetyl, that will be condensed. But this reaction is unfavorable thermodynamically. It requires a lot of energy inputs. So you ask yourself that in this reaction, malonyl is going to undergo what you call oxidative decarboxylation. So the decarboxylation tells you the fact that we are going to lose CO2, right? Very good. Why would the body add a carbonyl group from bicarbonate to an acetyl unit to form malonyl, and then add CoA to form malonyl CoA, and then come back in another step and want to remove the CO2? Now, I made mention of the fact that this reaction is what? Unfavorable thermodynamically, is an endothermic reaction. Or elsewhere you see endogonic. Because it is this way, and the body can't expend ATP in doing condensing these two acetyl units, because this thing is going to repeat a lot of that. That means a lot of ATP will be used. So the body goes through the formation of malonyl, and then when it comes here, it undergoes the oxidative decarboxylation and releases energy. And then when it releases the energy, so that means that the oxidative decarboxylation is what? An exothermic process. It's going to release energy, and that energy is used to what? To drive what? The condensation of these two acetyl units. Now, upon this condensation, we are going to get the compound called acetoacetal ACP. Let me get this. Acetyl ACP, right? So we are going to do away with CO2. So acetyl ACP, I've already mentioned the enzyme. So that is the intermediate at the end of what? The condensation reaction. Now, the second reaction we made mention of was what? A reduction reaction. If you remember your redox law, there are three things that account for what reduction. One, either you are accepting electron. Two, you are what? Gaining hydrogen. And then three, you are what? Having a removal of what? Oxygen. Now, any of this happens, and then we are looking at what? Reduction. So essentially that is what occurs. Now, NADPH that we said earlier, that we either get it from malic enzyme, most of them in this pathway, or from PPP, pentose phosphate pathway, or the hexose monophosphate shunt. Or what? Donate this electron. Donate it to what? Acetyl ACP. Now, when it donates it to it, then a reduction occurs, and then we end up with the intermediate D-beta hydroxy butyryl ACP. Hydroxybutyryl ACP. Now, the enzyme here is a reductase, and the name is beta ketoacyl ACP reductase. That is the enzyme that is going to do this job for us. So D-beta hydroxybutyryl ACP is a resulting intermediate through the reduction reaction. Now, in the third step, that is a dehydration reaction. What is going to happen? The dehydration means you are going to remove water. Now, this removal of water is going to introduce a double bond, specifically a carbon-carbon double bond. So you introduce a double bond by dehydrating the hydroxybutyryl ACP. So when you dehydrate it, we are ending up with a compound called protonal ACP. Now there is another name for this. It is the same as trans delta 2, but enoyl butynoyl ACP. Yes, trans representing a sort of the geometric isomer, sorry, and then the delta 2 is given as the position of the double bond. We made mention of the fact that there is a carbon-carbon double bond that's what will be introduced. Okay. Then enzyme over here that is going to do the job for us is beta hydroxy acyl ACP dehydratase. Elsewhere, you will see dehydratase. You see dehydratase elsewhere to other literatures too. So whichever goes for you. So it's beta hydroxy acyl. Hydroxy acyl. So hydroxy acyl. Yes. ACP dehydratase. That's going to do the job for us here. Now we have the butynoyl ACP, and then there's a double bond in it. We are not forming an fatty acid that has double bond yet. So the fourth reaction intervenes by reducing the double bond for us. So reduction, another NADPH comes into the scene, donates an electron to the crotonal ACP, and then we end up with a compound butyryl ACP. Via what? Another reduction like this. And then the enzyme there is a beta enol ACP reductase. Now, we agree that palmitate is 16 carbons. And then at this point, we have but, that is what? 4 carbons. That is 4 carbons. Now, what happens is that we have to what? Extend what? The chain, right? So ACP now carries this butyryl ACP that we have here from the active site of beta enol ACP reductase back to the very first enzyme in the what? The condensation reaction. So we're coming to look at that. So we made mention that we have beta keto acyl ACP synthase, right? So that's the first enzyme. ACP is going to take butyryl ACP to this place. It takes it to this active site and then leaves it over there. The butyryl becomes bound to a cysteine SH at the active site over here. Now, what happens? ACP goes for malonyl, and then what also brings it back to what? This active site. So right now you have butyryl and then what? Malonyl. Now the same way we talk about the condensation reaction in the very first step, that's the same thing that will occur. Malonyl will still go through what? Oxidative decarboxylation, leaving it with what? An acetyl unit, because it's going to release CO2. And then this acetyl unit now what's going to react with what? Butyryl ACP over here. So we no longer have a 4 carbon what? a 4-carbon fatty acid, but we are looking at what 6 carbons. We are looking at what 6 carbons. Now, with this happening, now this 6 carbon compound will now go through our second step of what? Reduction. Then it will go through dehydration. So the same enzymes for another reduction. So at this juncture, it has got what? The beta what? Enoyl ACP reductase. It's at this active site again. Now, all of this is happening because we want to achieve what? 16 carbons, right? And then we need what? And then we have what? 6 at this point. And then every cycle that we go through adds 2. So let's say from the formation of butyryl ACP, you will do 6 rounds of what? Adding 2 acetyl units. So 6 times 2, that will be what? 12, so that you can add to the 4 to give you what? 16. So you go through that reaction for 6 times, and then you come and end up over here again. And then at that point, we have palmitate. Palmitate. At this juncture, we are done. We have formed the 16 carbon fatty acid. We need to liberate it, right? But this palmitate is what? Linked to what? ACP. So the enzyme thioesterase, part of the fatty acid synthase complex, breaks this link and then what? Liberates what? The palmitate from ACP. But for this palmitate to undergo any metabolic reaction, it has to be activated, hence the addition of what? A CoA. So we have palmitoyl CoA. Is a CoA that would activate the palmitate. So when you add coenzyme A, it is able to be active, and then it can undergo what? Any metabolic, any reaction that is designated, be it what? Extension, or if you have more of the palmitoyl CoA, it's entering what? The oxidation pathway to produce what? Energy. So all that happened, you go through the cycles, and then you end up with palmitoyl CoA, and then there's liberation of palmitate from ACP by thioesterase, and then you complex the palmitate with coenzyme A, and then we end up with what? Palmitoyl CoA.